Hello and welcome to a video meant for Calculus 2 on trigonometric integrals other than sine and cosine. And in this video, we're specifically going to look at the cosecant and cotangent powers of those functions. So before we do that, let's take a minute over to the side here and sort of brainstorm some of our derivatives involving cosecant and cotangent, as well as the Pythagorean identity that involves cosecant and cotangent. So if I started you off with the fact that sine squared x plus cosine squared x equals 1, we should know that we can take that Pythagorean identity and we can, for example, divide by cosine squared in every single term, and we would end up with the Pythagorean identity that deals with tangent squared and secant squared. And if we take the same Pythagorean identity and we divide through by sine squared of x, every single term, so sine squared divided by sine squared is 1, plus cosine squared x over sine squared x would be cotangent squared x, and the reciprocal of sine squared of x is cosecant squared x. Okay, so now let's take the opportunity to write our derivatives. So derivative with respect to x of cosecant x, and derivative with respect to x of cotangent x. So take a second, maybe pause the video, see if you can fill these in based on your Calc 1 derivative knowledge. Okay, and hopefully you got to the derivative with respect to x of cosecant x is negative cosecant x cotangent x, and the derivative with respect to x of cotangent x is negative cosecant squared x. And again, notation will become important, especially as you travel on through your calculus series when you get into multivariable calculus. Okay, so I'm going to need these. I'm going to need this Pythagorean identity, right? Maybe some rewrites in there as well. I'm also going to need to know the derivative, of cosecant and the derivative of cotangent. That way I can recognize their antiderivatives as well. All right, so let's head back over to our problem now that we have that kind of as a reference. So we are going to be working with the antiderivative of cosecant to the fourth of 2x times cotangent to the fourth of 2x with respect to x. So what I need to think about is I'm just trying to figure out a u du pairing so that I can write this entire integrand in terms of u, okay? So again, I can write u to any power, but the trick is I want to make sure that I have the correct number or power left for that trig function so I can use a Pythagorean. So for example, if I notice that if I use the fact that the derivative of cotangent is negative cosecant squared, think ahead, that's going to use 2 of those 4 cosecants, which will leave 2 left. Perfect. That's Pythagorean. So I'm going to say let u be cotangent of 2x. That way my derivative, as a function, it becomes negative cosecant squared of the angle, which would be 2x. But I also have to use chain rule multiply by 2. So this derivative becomes negative 2 cosecant squared 2x, and don't forget your dx. So now what I'm going to do is I'm literally going to rewrite my original integral here, and I'm going to say I can put a negative out and a negative in. Also, I can put a 2 in as a factor. I'm going to multiply by 2 if I put that factor of a half out. Because again, negative half times negative 2 is just positive 1. And the reason I know to do that is because I'm trying to make sure that my du is in my integrand. So I've got the negative 2. I'm going to split up these cosecant to the fourths, and I'm going to say it's cosecant squared of 2x times cosecant squared of 2x, because if I multiply those together, I just get cosecant to the fourth. And then I have times cotangent to the fourth still of 2x dx. Okay, So I will highlight here this negative 2 cosecant squared 2x and the dx all becomes du, so that's going to get used. The cotangent to the fourth of 2x is going to just become u to the fourth. That's great. So now the only question becomes, and you'll know you did this problem right, if your leftover product, or that trig function, cosecant squared of 2x, if you can write that in terms of your u. So can I write cosecant squared of the angle in terms of cotangents? And because of our unique Pythagorean identity over here, I sure can. Cosecant squared of 2x is the same thing as 1 plus cotangent squared of 2x. And again, cotangent is u. So this whole thing is going to become negative 1/2. All of the yellow just becomes my du. The negative 2 cosecant squared 2x and the dx just become my du. The 1 plus cotangent squared of 2x becomes 1 plus cotangent is u. So that becomes u squared. And the green cotangent to the fourth becomes u to the fourth. So I should just be integrating once I distribute u to the fourth plus u to the sixth as a quantity. So I'm going to power rule integrate this. So it's negative 1/2. I'll just leave that on the outside. U to the fifth over 5 plus u to the 7th over 7. Don't forget your plus c. And lastly, I will put my u back in. My u was cotangent of 2x. Okay, and there's my final answer. Now again, in some systems, if you are trying to type in cotangent to the fifth of 2x and it's not understanding it, that's fine. Just type cotangent of 2x. You can put the whole thing in brackets or parentheses and then raise it to the fifth. Just make sure ultimately that you don't just move the 5 to be right after the 2x, because then that's just raising your angle to the fifth. So it either needs to be after the cotangent function or after your entire trig function, cotangent of 2x, is in parentheses, then you can raise that to the power. So just watch out for that. Okay, let's do another one with cotangents. And this one is a definite integral, so I will spend some time at the end talking about all the different ways we can write this answer, because there certainly are a couple different options here. So if I think back, let me get my notes that we had. I'm going to move them down so we can see them. Okay, so all I did was copy down our Pythagorean identity and our derivatives down here so we have them as reference while we're doing this problem too. So the 4, don't let me forget about this, constant coefficient of 4 out here, but that certainly could be brought out front from your whole integral. Just don't forget it when you go to figure out your answer. So this is definitely powers of trig, but what I'd like you to make sure you understand is that if you're going to let u, for example, be cosecant of x, in your integral somewhere, in your integrand, you need to have the trig functions, negative cosecant x, cotangent x, because you have to have your du there as well. So if your u is cotangent, the same thing is true. Now I have to have a negative cosecant squared x somewhere in my antiderivative or somewhere in my integrand for that to work. So if I only have one trig function, if you only have cotangent cubed x, and your idea was let u equal cotangent x, because then I can just write it as, and I'll put the u in here, as 4 times u cubed, that's not correct because you do not have du here. Because if u is cotangent, du is negative cosecant squared x dx, and I don't have that anywhere. So that's not going to work. So the best thing that I can do is recognize Pythagoreans and recognize that I'm going to split up cotangent cubed and write it as cotangent squared of x times cotangent of x. And you may not even see exactly why right now, but I think after we finish this problem, you probably will. So, and again, the u du, they have different trig functions in the u as in the du. So I don't even necessarily want both of these products or both of these factors in this product to be cotangent. I want one of them to be cosecants. So this cotangent squared can easily be turned into cosecants. So look over at your Pythagorean. Cotangent squared x, if you solve for that, you would just subtract 1. So cotangent squared x is the same thing as cosecant squared x minus 1. Let's just distribute this cotangent into those terms. So my first term will become cosecant squared x cotangent x dx. I'm going to separate these into two integrals so we can see it. Pi over 4, pi over 2 are my bounds. And the second term would be minus cotangent x dx. So if I rewrite that initial cotangent squared x with cosecant squared x minus 1, and then I distribute that cotangent in, here I am. Don't forget your 4 out in front of both antiderivatives. I can actually integrate cotangent of x dx without any advanced knowledge. That actually is a Calc 1 integral because I can rewrite that as cosine of x over sine of x. If u is that denominator, then my du happens to be that numerator, because if u is sine x, the denominator, du is cosine x, which is exactly what I have in my numerator. And of course, don't forget your dx. So this antiderivative is really a du over u. So it will become natural log. I'm also going to change my bounds. I think that's really helpful here. So if x is pi over 4, u is, and I'll fill that in a second, and if x is my upper bound, pi over 2, u is something. And you're going back to your u statement. U is sine of x. So if x is pi over 4, u is sine of pi over 4, and sine of pi over 4 would be square root of 2 over 2. And if x is pi over 2, u is, again, sine of pi over 2. Sine of pi over 2 is 1. Okay, so I will write this antiderivative since we were working with the second one here. So this is du over u. It will become natural log. Let me put my u bounds on here. Read 2 over 2 to 1. So if I finish this one off, I get negative 4 natural log of u. You don't really need the absolute value bar in this case because you know both your bounds are positive, but that's okay. So minus 4 natural log of 1 minus natural log square root of 2 over 2. Natural log of 1 is 0. So if I distribute this negative 4, I do get positive 4 natural log square root of 2 over 2. That is something I'm going to hold because I don't want to lose it. That's the second part of my answer. So let's go back up to the beginning here, and I need to see how in the world am I going to integrate cosecant squared x cotangent x. So look at it for a second and see if you can find a u du pairing. I actually can. If u is cotangent of x, du, right? Look back at your cotangent derivative. We're here again. So if the derivative of cotangent is negative cosecant squared, all you need to do is multiply a negative in and a negative out. So u is cotangent of x. Du is this negative cosecant squared x dx. And so really what I have here is -4 on the outside. All right, and let's change our bounds. I'll do that here in a second, but I'm going to just write what I have in my integrand. The cotangent of x will be used by my u, so you can kind of make sure every part of your integrand gets used. That's my u. And the negative cosecant squared x dx was what we said was du. So I'm just integrating u, which I know to be u squared over 2. So ultimately, I know this part is just going to be -2 u squared. But again, I have bounds of integration. So if I change my bounds, let's see what our bounds become. So if x is pi over 4, u is, and I'll figure that out in a second, and if x is pi over 2, u is. And again, this time you're working with this cotangent of x. So u would be cotangent of pi over 4 and cotangent pi over 2.
Okay, so let's figure out this cotangent of pi over 4 and cotangent of pi over 2. Let's figure out what those side ratios will become. So I'm going to go off to the side here and just draw the 45, 45, 90 right triangle. Right, that's that pi over 4 angle of rotation. Most of you have learned this maybe on a unit circle where the hypotenuse or radius is 1. And if so, these sides are read 2 over 2 each. So cotangent of this, right? So it's reciprocal of tangent. Tangent is opposite over adjacent. So this is going to be adjacent, which is rad 2 over 2, over opposite, which is rad 2 over 2. So this gives me a u value of 1. So my pi over 4, or my lower bound, would have a u bound of 1. Now, cotangent of pi over 2 is straight up, so this is the point 0.01 on the unit circle. And again, if tangent is opposite over adjacent, we can think of it as y over x. So cotangent is going to be x over y, so 0 over 1. So this will give me a u value of 0. Now be very careful. Cotangent of pi over 4, this was my lower bound, right? So we did our lower bound first. So I put my 1 in the lower bound. And then when I plugged in x equals pi over 2 into my u equals cotangent of x, I got u equals 0. That's my upper bound. This will happen sometimes when you had to manipulate in a negative. Maybe your bounds will change, because I'm not sure if you remember. I'll write this on the side. If you have an antiderivative of a function from a to b, this is the same thing as the opposite of the same antiderivative from b to a. Because again, it's kind of like saying 2 minus 5 instead of 5 minus 2. They're just opposites. So 2 minus 5 over 5 minus 2. The first one's -3. The second one's +3. So that's why that works. Okay, so I can keep my upper bound 0, keep my lower bound 1. A lot of us do forget, though, to put the 0 in first. So if that's the case, you can just get rid of that negative right there. But my lower bound is 1, upper bound is 0. So if I do that, 0 squared minus 1 squared, I do get -2 distributed times that -1 will be a +2. So I had the other answer over there, so I'm going to have 2 plus, and I'm going to work and show you all the different ways that we could actually write this answer. So the answer in exact form is 2 plus 4 natural log squared of 2 over 2. That's a perfectly fine and acceptable answer, but sometimes the answer that we're looking at or seeing might not match that. So let me just take a second and show you why not. Well, a couple things here. This coefficient of natural log could really be represented as the exponent. Do you remember that from your natural log properties? So this could be like so. And then I'll raise each one just so you can see it. Square root of 2 to the 4th over 2 to the 4th. Square root of 2 to the 4th is 4 square roots of 2. So that's really 2 times 2. right? Because it'd be square root of 2 times square root of 2 and square root of 2 times square root of 2. So 2 of those square root of 2's make a whole 2. So I have in the numerator 4, and in my denominator 2 to the 4th is 16. So that's 1/4, and I'm trying to show every step along the way. Some of this you might be able to do maybe in your head, but just trying to show it all out. And then we also should remember a natural log property when we're dividing, right? So think about when you're dividing with the same base, x to the 5th divided by x squared, for example, you subtract those exponents. And since natural log solves for an exponent, our natural log properties resemble our exponent rules. So here I am dividing, right, with the same base. So I'm dividing, and that will turn into a subtraction. So it'll be natural log of 1 minus that natural log of 4. Natural log of 1, as we said, is 0. So I could see as simple of an answer as 2 minus natural log of 4. You can certainly test this in our calculator, and let's just test it real quick so we can make sure that our answer is legitimate. Okay, so first things first, I just use Desmos for this example to show, but if I go to any calculator and type in to try to get the decimal version for 2 plus 4 natural log the square root of 2 over 2, I get this decimal, this 0.6137, etc. And if I go to type in any of these steps or lines along the way, I should get that same decimal. So when I'm all the way done and I got an equivalent expression of 2 minus natural log of 4, you can see there that those decimals are equivalent. I can also use Desmos if I wish to check my original antiderivative. So we had INT for integrate, and now I've got the original integral in my screen. My lower bound was pi over 4. I just typed pi for pi. There certainly are other ways to do that. Pi over 2 is my upper bound. And I'm integrating cotangent cubed x. And notice it's not giving me any decimal values here. Well, that's because it doesn't know who it's differentiating or anti-differentiating with respect to. It also doesn't like the fact that I typed in cotangent cubed in that way. So what I will do is put cotangent of x in parentheses and then cube it. And I will put the 4 out front, just so you can see what that looks like. You could have certainly put it inside of your antiderivative. Just be careful that you don't put it inside of the function that you're cubing. So either place you put it, you can put that times 4 inside your integrand. Just again, don't put it inside of that cubed. So I hope you found this video on cotangents and cosecants and integrating powers of those trig functions helpful. Thanks for watching. Have a good day.